So welcome back to this second part of chapter 4. So we are continuing with probability. We are going to look at a few more definitions. So generally you can have an event. An event is basically a collection of sample points. So sample points is when you have, for instance, an experiment. We say that an experiment is something that has well-defined. It is a process with well-defined outcomes. Yeah. So each outcome is a sample point, and a collection of different outcomes gives you an event. For instance, you could have, let's say you're tossing a coin as you experiment. So let's say this is your experiment. So let's say this is a multi-step experiment. So if you're tossing a coin, let's say twice, yeah? Let's say you toss a coin twice, and you want to find, you basically want to find a probability that you get 2 heads. Probability that you get 2 heads. So this getting 2 heads is basically an event, yeah? It is a collection of sample points, and the sample points that you're looking at are HH, right? Because if you have 2 tries, you can get H and T in the first try. You can get T and H, rather T and H in the first or second try, or you can get all tails, or you can get all heads. So a probability that you get 2 heads. So for instance here, the probability that you get 2 heads is going to be 1 over 4. Yeah. Maybe you could toss this 3 times. So you could have HTH, you could have THT, you could have TTH, you could have HHT, you could have, so those are the ones that begins HTH, you could have HHH, you could have TTT, you could have, did you have HHT? You could have THT, you could have HT, H, so there should be 8, yeah? So in this case, you know that the number of outcomes is going to be, because we have only 2 options, so it's going to be the sample size, the sample space, the space of the sample space, if you're dealing with such, and space of the sample space should be, so the size of the sample space, if you have such an experiment, it should be the number of outcome, it should be the number of so it should really be so this should be, so the number of outcomes by the number of tries, number of steps. So for instance here we have 2 possible outcomes. So if you do this 3 times, you should have a sample size of should have a sample size of 2 to the n. So you have 2 to the n, yeah, where n is the number of tries. So if you have 3, that should give us 8 possibilities. So for instance here we could be interested in the probability that you get 2 heads. So here our probability that you get 2 heads is either that, or that, or that. So it's that, HTH, it is that, and it is that. So in this case it's going to be, so probability that you get 2 heads, if you have 3 steps, then it's going to be 3 over 8. Yeah. What about the probability that you get at least 2 heads? So this is 2 heads and more, right? So you're gonna get that, then you're going to get that, then you're going to get that, you're going to get that and that. So this looks like this is going to be 4/8, which is a half, 0.5, right? So not too much to say about this. That's basically the probability of an event. It's really going to be the sum of all the sample points within the event. So there's some basic probability relationships you could look at. There's what you call the complement of an event. So the complement is simply the probability that the event does not happen. And obviously, this means essentially that if you have, it means essentially that the complement, if the event is A, the complement is, for instance, the event is H, so then A complement plus, maybe let me just write it, let me write out everything. So probability A complement plus the probability A should really give us 1. And also the probability of I think this should really be obvious, of A complement, assuming you know a probability of A complement, then it should really be 1 minus the probability of A. So for instance, if I know the probability that I'll pass, then the probability that I won't pass should be 1 minus the probability that I will pass. So the complement is the opposite of the, so just like how you have complements in sets, right? So if you have to put this in set balance, for instance, because we know the union is 1, right? If you look at probability, the sum of all our probabilities should be 1, yeah? So it's really, if you take it back to set interpretation, then it's really the same thing, because the union must be the set plus its complement should give you the union. So the complement, if you want to recover a complement given the union and the set, then it is the union minus that set should give you the complement of the set. So let's look at addition law. So the addition law is how do you get the probabilities of unions? Yeah, how do you get the probabilities of unions? If you want to get the all the events in a more than so if you want to get all the events in a union, rather all the sample points in a union, so you want to set a probability that that two events occurred. So that's going to be a probability. Let me use the equation editor. So probability of that A and B occurred, yeah? So that A or B occurred actually, yeah? So this is, so the addition law, to get the probability of A union B, you should get probability of A and the probability of B minus the probability, because you don't want to double count, probability of A intersection B. Actually could have gotten the union operator from here. So that gives you the union. So this is the probability. So this is the addition law, which gives you the union of two probability of two events. So of two event sets. I should call them event sets, right? So if you have a mutually exclusive, events, then you have no union. So in other words, so events are mutually exclusive. You have no, you don't have any union. So you have, So for instance, you can the probability, assuming, of course, because if you're voting and you have a valid vote, one of the rules is that you have to select exactly one candidate for each. You have to select exactly one candidate for each position. For instance, you cannot vote Chagulanyi and Museveni at the same time and still have a valid vote. So in that situation, you have what you call a mutually exclusive event, because one implies that the other did not occur. So if you have mutually exclusive events, probability of A union B for the mutually exclusive events, let me just see if I can get an accent or some kind of a script. Limit. Okay, I think there's nothing. Maybe an operator. Okay, so probability of A union B for the mutually exclusive case is really going to be probability of A is still probability of A plus the probability of B, yeah, minus the probability of A intersection B, but because you do not have an intersection, this means that it is still going to be, this is essentially just the probability of A plus the probability of B. So this is what happens when you have no intersection. It means that the probability of A union B is really just the probability of A plus the probability of B. We can look at the conditional probability. So conditional probability is the probability of some event given another probability of some event given another event. I'm just looking for the bar operator on my keyboard, which I seem which I'm having difficulty finding. Bar operator, the bar operator. So maybe let me use this for a bit as I try to figure out what that is on my keyboard. So a probability of A given B, so if you're doing conditional probabilities, this is the probability of A intersection let me use the equation editor. So conditional probability, insert a new equation. So probability of A given B, I will say this is the it's writing it as a fraction. So let me see if I have anything here. I need a bar operator. Okay, I think I got it. So probability of A given B, right? Probability of A given B is really the probability of A, is the probability of A intersection B. So both A and B have to occur, right? Given means over the probability of B. Right, so this is really what it means. If your probability of A given B is probability of A, and that A and B occurred given probability of B. So you can actually visualize this using a cross tabulation. For instance, here we have some data of men and women being promoted, right? So you have this kind of frequency distribution, conditional probability distribution. These probabilities within the table are what we call the joint probabilities. We call these the joint probabilities. Yeah, the probability, for instance, that one is okay. In this case, we have it in the frequency distribution as a frequency distribution, but we can convert this into frequency distribution. So if you convert it to this kind of, so this 0.24 is coming from, so this is the sum, the overall sum, yeah. So for instance, if you go back here, if you wanted to compute the probability, so this is data of promotion, given one is a man or a woman, right? So let me just get this formula thingy. So when you set the formula, you set the new equation. So the probability here, so I'm going to use the empirical approach, that one was that one was promoted given the that one was promoted and they were men. Oops, did I get the right symbol? It looks very one is promoted and they are men. Is going to be given by probability that one is, so it's going to be given by this number, yeah, which is 288 over 1200, and that should give us so this is how we convert these values to probabilities, assuming we already have these numbers, yeah. So that should give you 0.24. So that's how we are obtaining the values. This is how we're obtaining this table, yeah. So we're dividing everything by 0.2 by 1200, which is the value in the bottom, corner, the bottom diagonal here. So if you divide everything out by 1200, we should get these kinds of probabilities, yeah. We should get these kinds of probabilities. We've already done independent events. So these probabilities give us the probability that something is given, and this, what we see here in the margins, is what we call the marginal probability. For instance, this probability over here, when you marginalize, you are actually considering a single option, yeah. So that's why you call these marginal probabilities, and this in here are called the joint probabilities. These are the intersections, right? So the joint probabilities, so sometimes these are written like for instance, if you look at the, so for the joint probabilities, you'll have different notations. So if sometimes this is written the probability that one is a man and is promoted, right? So this is really the probability that one is a man, intersection, the one is a man, intersection, one is promoted. Why does it come out like that? Now one is a man and is promoted. Okay, let's just go with that. So yeah, so this can actually, operate like that. It really means the same thing. So this is the joint probability or the intersections. Now, if you're looking at the conditional, what we refer to as the conditional probability. So the conditional probability is the probability given given some event. So for instance, if you look at the conditional probability that, for instance, 1 is a man, given 1 is a man, then it means we're going to marginalize out this column. That's what it means, to marginalize out the common. Remember, I told you the marginal probabilities are this, yeah? So to marginalize is actually to ignore women. So if you're going to marginalize out men, then it means you're going to ignore the case that people are women, yeah? So given that 1 is a man, what is the probability they're going to be promoted, yeah? So what is probability that 1 is insert new equation. So that's the probability that 1 is promoted given they are men, is going to be the probability that 1 is a man. So did we already have this somewhere? Yeah, so it's going to be this, yes? So it's going to be the probability that 1 is first of all is a man and is promoted. It's going to be the probability that 1 is a man. Oh, sorry. So it's going to be the probability that 1 is a man and is promoted. And is promoted over the probability that 1 is a man, yeah? So the given part is always in the denominator. So it basically means that we are going to ignore all these other probabilities of women. So this will give us the probability. So it's going to be the 0.24 that you see over here, man and promoted, 0.24 divide by the 0.8. This is going to give you 0.24 divided by 0.8, 0.3. So what do you really use this? For instance, if you want to compare, let's say some women have sued that they are being discriminated in promotions, and then you are maybe the defense lawyer. So to actually show this empirically, you don't simply go and say, well, according to this data, you don't simply look at the joint probabilities. You say, according to this data, probability that men are promoted more often is 0.24, and the probability that women are promoted is 0.3. Because then you are not considering the overall population metrics. Remember that men are 0.8. Yeah, men are 4 times more numerous than women. Yeah, so if you want to actually figure out if it is true that there's a preference for men to be promoted, then you have to normalize these values by their relative frequencies in the data. So to normalize the values by the relative frequencies in the data is simply to say that you want to make sure that you incorporate the fact that men are more numerous. So that's what you're really doing here. Yeah. So if you look at, for instance, the probability now that women, look at the probability that 1 is promoted given they are a woman, then it's going to be the probability. So it's going to be the probability the 1 is promoted, probability that 1 is promoted, promoted and is a woman, over the probability that 1 is a woman, right? The probability that 1 is a woman, which should give you point 0.03, yeah, 0.03 divided by 0.2, and this should give you maybe 0.03 divided by 0.2. which is 0.15. Yeah, so in this case you actually have a case. Yeah, so in this case you actually have a case, because if given I'm a woman, I actually have half my chances of being promoted, actually half. Yeah, given that I'm a woman. Yeah, so but if you're a man, you actually your chances of being promoted are 0.3, so you have a higher chance. It's twice the conditional probability is twice. So here there's actually a case to answer that probably you're having differential treatment when it comes to promotions. So this brings us to what we call the multiplication law. The multiplication law. So you have what you call the multiplication law. So I just want to have it formatted like that. So the multiplication law basically will give us the probability of the intersection, right? So it comes directly from this conditional probability. So if you want to get the probability, so if you want to get the probability of A and B, of A and B given some conditional probabilities, it's going to be the probability of A given B, probability of A given B times the probability of B. So this comes directly from this expression for the conditional probability. So if you want the probability A given A and B, the joint probability rather, yeah, then it's going to be a probability of A given B times the probability of B. So we can now go into Bayes' theorem, which is going to be really just an extension of this idea of conditional probabilities. So Bayes' theorem, for instance, if you want to know the prior, if you have some events and then we want to adjust their probabilities given new evidence, yeah, we want to adjust their probabilities given new evidence, then we can compute. So that basically is what we refer to as computing the posterior probability. So we start off with prior probabilities, which is what we know about the population. So if you have some new information, say for instance, I know about probability. Let's look at the quality levels of two suppliers. So here we have two suppliers, yeah, supplier 1 and supplier 2. Just to show you how you use this Bayes theory. So you have two suppliers, so probability of so the probability that something is good, that's 0.98, that's 0.92. The probabilities for these suppliers, percentage good, percentage bad. Okay, anyway, let's say the probability of good given. So the probability of good given supplier 1 is equal to 0.98. Yeah. Then the probability good given supplier is 0.95. Yeah. Actually really can't know this because this is incomplete data. So this is giving us the probability that it is good, and let me see if we can get the full data for the situation, for the case. What are the frequencies for these suppliers? Okay, so we also need these frequencies for these suppliers. In order to compute the, so these are the prior probabilities. Did I have that? Okay, I don't really have them here. So let's let me just copy this. So these are the prior probabilities. That is a probability that it is supplier A is 0.65, yeah, and the probability that is supplier B is 0.35, yeah. So that gives us more information so that we can try this case. So supplier A is so probability good given supplier is 0.98. Then probability of supplier 1 is 0.65, and the probability of supplier 2 is going to be 0.35. Now assuming we pick up a part and it is bad, yeah, what is the probability it came from a supplier, from supplier 1? So for instance, if you want to compute the probability that some part is bad given supplier 1, yeah, what is the probability that some part is bad given supplier 1? So this is actually going to be the probability that it is bad and it is indeed supplier 1. Let me just get a formula for this. So really what we want to compute in this case is we need an equation. So an equation. So this is really going to be the probability that it is bad and coming from some supplier 1. We need to insert we need one of those, and it's coming from supplier 1 over the probability that it is coming. So a probability that is bad given supplier 1 so given that it's bad, why is it coming? What's the probability that it's coming from supplier 1? So we want this kind of probability, or rather, sorry, what is the probability that it is from supplier 1 given it's bad? So over the probability bad, and this is going to be, so our probability is bad given supplier 1. This over here we can get with the multiplication rule, and that will give us so from the multiplication rule we know that probability something, the intersection is going to be the probability that is bad given supplier 1 times the probability supplier 1 over the probability it is bad, yeah, the probability that it is bad. So no fireworks here, really, there's no fireworks here, but then in what situations is a product bad? So if you have only two options, for instance, in what situations is a product bad? If you have only two options, a product can be bad, so the numerator remains the same, the probability that it is bad given it came from supplier 1 times the probability of supplier 1 over the probability, over this probability, because there's only two cases when a product is bad. It's either came from supplier 1 or it came from supplier 2. So it is going to be that probability. So the numerator is actually that probability that it's bad, plus this probability that it is bad given supplier 2, that it is bad and it came from supplier 2. Yeah. So if you have a two option kind of, you know, situation, then this is going to be the actual probability. So typically you're going to use A and B, right? It's going to be A and B. So maybe let me just make this in this kind of but given, and let me just leave it like this. There's really no problem. So if you had three suppliers, and you wanted to know the probability that it is bad given some supplier 1, so this would actually continue. The numerator would continue, yeah. So the numerator would continue. It means you'd have some additional scenario, something like that, yeah. So this is Bayes theory. So given that you pick a part and it is actually bad, you want to know the probability that it actually came from a particular supplier. So this basically would, and this is basically how you compute it, and it is directly as a result of these other things that you are looking at, the conditional probabilities and the multiplication law. So this brings us to the end of chapter 4.